Welcome to lesson 7.1 and 2. You'll notice that these notes look different. In the past, you've been given PowerPoints. These you can print off a Word copy of the notes and kind of follow through and do the problems as we work through them. So let's start off with just talking about electromagnetic radiation. Electromagnetic radiation is how energy travels through space, empty space. A lot of times we just think the sun provides us with light energy and thermal energy or heat energy, and there are so many more different types of energy that it provides us with. Those waves exhibit wave-like behavior. That energy exhibits wave-like behavior, and it travels at the speed of light. So if you'll look down characteristics of waves, wavelength and frequency is one of the things we talk about. The distance between two consecutive peaks or troughs is considered a wavelength. Frequency is the number of waves or cycles per second, and it appears as if there it is, there's my document, that the lambda sign stands for wavelength, the nu sign stands for frequency, and then C represents the speed of light, which is always a value that is given. Wavelength must be measured in meters, frequency in cycles per second, or a unit called hertz. And then the speed of light is given there as 2.9979 times 10 to the 8th meters per second. This is the electromagnetic spectrum. There are lots of different types of wavelengths on the electromagnetic spectrum. It goes from gamma rays clear down to radio waves, or a lot of electromagnetic spectrums will show them in the opposite order with radio waves on the left and gamma rays on the right. Either way, you can see how the wavelength changes when you get to different types of energy. Practice problem number 1 asks you to take the wavelength of the red light in strontium, and determine what frequency that red light is exhibiting. So first, over here in the red ink on the right hand side, you'll notice two different equations set up, or two different dimensional analyses set up. They both say the same thing, but it's just a different way of representing nanometers and meters, that unit conversion. And so you have to convert those to meters first. And I just now noticed that that negative should not be there on that 2. It should be a positive 2. So please ignore that. And if you do that calculation, please use that as a positive 2. So anyway, we calculate the wavelength as 6.5 times 10 to the negative 7 meters. We plug it into our equation, and we calculate our frequency to be 4.61 times 10 to the 14th hertz. The concept check question: which form of electromagnetic radiation has the shortest wavelength? If we scroll back up, then we will see that gamma rays are on the left-hand side, and they are a lot smaller than radio waves, which are on the right-hand side. Okay, so let's move back down here. Max Planck, a German physicist actually, he postulated energy can be gained or lost in only whole number intervals of h times v. H is his constant, Planck's constant, 6.626 times 10 to the negative 34s, and his change in energy can be represented by that equation there. Planck's postulate, it goes along with what we kind of know about the atom. We know that electrons can only occupy certain energy spaces. It's not necessarily orbital like Bohr's model over here, but there are specific places. And so when it loses or gains energy, it can only lose or gain energy which would account for a rise or a fall from one or the other of those energy levels. Energy is quantized. A quantum is a packet of energy. And as Planck said, energy can only be transferred in whole quanta, so it seems to have particulate properties. So at the very beginning of this Word document or this PDF, you saw that it had wave properties. Now to also see that it has particulate properties. So we're going to use, on practice problem number 2, we're going to use the equation for the velocity of a wave to calculate the frequency, and then we're going to use that frequency in Planck's equation. So blue color in fireworks, often achieved by heating copper 1 chloride to about 1200 degrees Celsius. Then the compound emits a blue light having a wavelength of 450 nanometers. What is the increment of energy, that quantum, that is emitted at 4.5 to 4.50 times 10 to the 2 nanometers? So again, we had to turn our 450 nanometers into meters, so that's there. And then we used the speed of light, and we got a frequency of 6.662 times 10 to the 14th. Plug that in over here, took it times Planck's constant, and then it wants to know the increment. So we're just going to say there's one energy level, so that's where we're going to put a 1 in there, and we're going to calculate it as 4.41 times 10 to the negative 19 joules. So when we started talking about waves behaving as particles, then Albert Einstein jumped in and said that actually electromagnetic radiation is a stream of particles. And then he gave an equation that said the energy of each photon is given by the particular equation I just highlighted. Photoelectric effect, you can read more about that in the text, but it's more about which electrons are emitted from the surface of metal when light strikes it, and that's how Einstein did a lot of his studies on light. Einstein's theory of relativity, he proposed that energy has mass, and his famous equation is E equals mc squared. Also came up with the dual nature of light, whether it's a particle and a wave. De Broglie did another equation. De Broglie ascertained that matter is assumed to be particulate. It exhibits wave properties. And so in determining the mass, we use Planck's constant, we use the wavelength, and we use the velocity. And notice that in this case, that's not a frequency they're looking for, it is a velocity. And so the practice problem number 3 asks you to compare the wavelength for an electron traveling at a speed of 1 times 10 to the 7th meters per second with that of a ball traveling at 35 meters per second. And so we went through those calculations, calculated the, oops, sorry about that. Get rid of that. Went through those calculations, used de Broglie's equation, set the mass equal to the wavelength times the velocity. I'm not sure what's going on in this part here, but we'll see if we can move that a little bit. Every time I move it, I get a, yeah, there we go. Get that back. So where electron is in green, plugged in the numbers to the equation that's highlighted above. Baseball's in blue, and we figure out that the wavelength of a baseball is much, much smaller than the wavelength of an electron. And then the last part of these notes talk about diffraction. And diffraction results when light is scattered from a regular array of points or lines. Colors result because various wavelengths of visible light are not scattered in the same way, so that's why we see different colors. Sometimes we see a diffraction pattern, and with that diffraction pattern, that's going to move us on into Bohr's model of the atom and why he saw 4 lines with hydrogen using a diffractometer. So that concludes lesson 7.1 and 2. We'll move into Bohr's model here shortly, and make sure you print off it so you can kind of follow along and do the math yourself, perhaps even before you look at these notes.